We are live.
Hey everyone, welcome to another Wolfram Institute Live Science stream. Today we're continuing our conversation with Carlos on the work that he's doing regarding complexity categories, uh, general advancement of the theory of hypergraphs in order to better develop a framework for this study that we're conducting regarding this kind of emulation or passing between formal systems and the complexity trade-offs, algorithmic complexity, behavioral complexity that one incurs when one emulates from one system to another. So I don't think we're going to do that much review, if that's all right with the viewers. I think there are some problems that Carlos has encountered today that we're going to address. There are some problems that Nick has also encountered today that we're going to address. And honestly, that's good. When people are, I mean, there are many problems that you will encounter when you do research. And so when I hear, oh, we've hit a problem, for me, it's like, okay, good, things are being done. So yeah, Carlos, let's jump in. Tell us about your problems.
Okay, so I've got many problems, luckily only a few about hypermatrices and hypergraphs. So let me try and share this thing. Actually, this is probably not where I wanted to start. Let me see if I can navigate my way.
Hypermatrix algebra from hypergraph adjacency.
Wait, hide. If I go up here and I go this one, I think this is the one I wanted. I'm gonna make you guys bigger for the audience.
Okay.
So basically the two, I'm gonna quickly get to the roadblock, but basically these are two, I don't want to say dead ends, but like two blocks that I found, two abstractions that I found. So last time we agreed that we're gonna look at this particular operations of hypermatrices.
The cone.
The cone, blades, and three-fourths, because they're particularly symmetric and they kind of generalize matrix multiplication. And so by fixing some sequential expression for each of these, meaning you take these indices in a tuple, right? Not just in a sort of unordered colored list or whatever. And you define, so maybe I can do a pointer thing with some color. Or yellow maybe. So we basically define these as the sort of ternary operations for matrices over, sorry, that's a bit out of the screen. So those are sort of cubical matrices, right? Now, as we discussed, there's kind of four notions of identity, no longer just one, so I'll make that a bit bigger. There's four notions of identities. There's the more sort of standard one, which is basically the Kronecker delta as we know it. And then there are three of them, I1, I2, I3, which are basically just stacks of binary identities in each of the directions. So I've done some checks and I could find the identities exhaustively on these products. And so you have these particular patterns. I mean, these patterns are kind of wonky, kind of interesting. So, for example, this one is the gamma, the cone identity behavior, right? Which basically doesn't involve the Kronecker delta identity at all, right? So it's just 2, 3, 2, 1, 3, 1 identities. So okay. Then there's the beta one, which is similar, but it just involves the 1 and 3. Because, I mean, this is, the fact that it's 1 and 3 is basically an artifact of the sequentialization choice that we made, but the point is that there's only two of them. And then there's the 3/4 one that has a partial identity and a full identity in these combinatorial positions. So these have been searched computationally. Like these are all the possibilities that you can find with a fixed sequentiality, right? So this is kind of a semi or pseudo roadblock in the sense that, okay, what do you do with these identities? Not obvious. So instead, let's look at the cone problem, and this is something that is, as I said, there is literature about this, so this is not my idea to go into this direction, but I thought it would be a good idea to, like, for everyone to see what the logic is here, right? So take the gamma product, right? So one way to understand the gamma product, there are several ways that you can fit the gamma product to like, you can take the gamma product to fit some narrative, right? So there's a particular narrative that is quite compelling mathematically, which is to think of skew fields, right? Skew fields or skew rings are non-commutative rings or fields, right? So basically fields where your multiplication is no longer commutative, right? So you want to distinguish between left and right multiplication. And so it turns out that the gamma product, the cone product, basically models general linear combinations of skew linear combinations, meaning linear combinations that require distinction between left and right multiplication. And these few formulas are trying to express this. Right? So this formula here is basically a general bilinear combination, right? So if you have sorry, not bilinear, skew linear, sorry. If you have y and x as vectors, right, scalar vectors made of several scalar entries, then you basically want to have an index for B and an index for A, which essentially has to be common because this is just going to be a repeated thing for each entry, and then you want to have a SAP, another index that is running over the entries, right? So remember that in this is just the analog of what you normally write, something like, you know, yi equals sum over p of a I p x p, right? So I'm literally just adding something else at the back, right? Some b at the back, so because you have to distinguish left and right multiplication. So if you just enter 0 index values or 1 index value, some sort of single value in the missing indices, you can actually recover the gamma product. I mean, it's just an exercise of like noticing that if you move them around and you just check that by putting j equals 0, k equals 0, this expression actually reproduces the expression above. And that expression is exactly the formula that we had up here for the cone product, right? It turns out. So what you end up with is that, so it's a nice observation because you end up with that, you know, y as a vector is given by AB applied to X. So you can effectively have this sort of action like you do with matrices that act on a vector, right? So, but in this case, instead of a single matrix, now it's a pair of cubic matrices that act on a single vector, right? Mm-hmm. Okay, so this actually leads naturally, because it's a kind of an action, I mean, there's a group structure behind, like at least a monoid structure, so these things compose, right? Oh wait, I'm getting an error from YouTube or Twitch. Oh no, I think it was just local. Yeah, it's just local in the browser, no problem. Okay. So yeah, and so because you can define something like a monoid or a group, you can define invertibility, and so you can say that AB, the order pair, is invertible when you find another order pair, A dash, B dash, such that, you know, when you post-compose with the second pair, you get identity as an action, right? So you act X with AB, then you do AB, A dash, B dash. So that formula is basically this formula here, right?
Which one? Which one?
This is the formula that codifies invertibility here, right? So it's a double product, like usually inversion is, right? Like a double product with your binary operation, but now it's a ternary operation, and it's basically saying AB applied to X, then A dash B dash, and you get back X, right? Now, so this is very natural because this suggests that the eigenvalue problem in skew fields is formulated with this product in this way. So because now we are regarding that A and B act on as a pair on X, then there's this natural question of to what degree is this equivalent to just multiplying by scalar, right? But now because we are in a skew field and we have to distinguish left and right, we write this kind of formula, right?
Yep. Okay.
So
Two lambdas.
yeah, two lambdas,
Okay.
one per
One for left
side.
and one for right. Yeah.
So the problem here, so I wanted to illustrate this to say that yes, there's natural ways into spectral theory here. Like this leads us quite directly into a kind of spectral theory that is actually known, because this is non-commutative polynomials, and there's some work done, but it's kind of not super developed. The problem is that it kind of takes us away from hypergraphs, right? Like, because the problem is that we've confidently kind of gone into this direction, and then we said, well, to interpret this as a linear combination, we have to think of skew fields. And the problem is that most reasonable scalar rings or semi-rings or fields that we're going to use in our hypermatrices are going to come from adjacency data of hypergraphs, and any reasonable ones are going to be commutative, right? So this skew property is going to be quite strange to just get from the hypergraphs in a natural way for a vast number of applications. So I wanted to mention this because at this point you could go off and try to do some spectral theory here, but I think you will be lost in some abstract algebra that might not relate very immediately to hypergraphs, right? So just wanted to have this, people know about this, and now move to the more hypergraph related stuff that I think is
wait.
Sure, yeah.
I mean,
yeah.
So the question is,
what was it?
I remember at the end of the last meeting, you had suggested that while the blades in the Triforce case, the spectral theory was not really developed, it could nonetheless be explored, say, experimentally. But in the case of the cone, it was kind of known. If I understand, is what you're suggesting now that these skew field considerations actually kind of, are you suggesting that the spectral theory actually is somewhat underdeveloped, and that we'd have to develop it, and that itself would be its own task, which is unknown in difficulty and could lead us astray?
Yeah.
Or but what should I conclude from that basically there's no kind of readily available spectral theory for us to use, one that doesn't involve kind of spectral theory development on our part?
There is, so I didn't say that the spectral theory was known, but I did say that there is literature on this spectral theory. Right?
Yes.
So because
that's fair. Yes.
These are maybe in some realms they are the same statement, but in this realm it's quite different, because there is like maybe 5 papers at most, probably only 2 or 3, but I would say 5 to be safe. There's like 5 papers on the spectral theory of this kind of multiplication, right? These are papers that are specifically about the spectral theory of this matrix multiplication, of this cone hypermatrix multiplication. There's some other literature on invariant forms for non-commutative polynomials that you can relate to this by this kind of skew field combinations and linear combinations and so on. But the issue is that the relevance of my point of making this explanation is that this is kind of how the spectral theory that is known and is developed is motivated.
Mm-hmm.
Like the people who develop this theory, motivated in this way, they say, well, we're going to regard these things as acting on vectors. Now, if you want to see this as an action on vectors, you have to kind of believe that you can be skew. You can. These are well-defined actions anyway, but in order but the problem is if you are commutative, right? These actions kind of collapse because A times B becomes a single. You can move your scalars around, so you have some indexed object times some vector, and so you essentially you can package your eigenvalue problem in this ternary or higher order eigenvalue problem into a usual ordinary eigenvalue problem, because you can package everything into a single matrix, right? So the issue there is this doesn't really illuminate anything of what we want to do, because we want to look at hypergraphs that are completely general, and this is somehow assuming that you're going to have some situation where your adjacency can work out in this way. So my suggestion is, what I've done in these days is I've reviewed these papers and I wanted to summarize what the motivation is to kind of give a summary of like, this is probably not the most immediate thing we should be looking at this point.
Well, so what do you suggest as an alternative?
Yeah. So that's the one.
And by the way, I just want to mention, right, for issues such as this, you see, I would say when we encounter an issue such as this, I would say we really have two options. One is, as an organization in isolation, we can make the assessment that it's not worth pursuing because we're worried about the costs and we're worried about derailing the project. However, we've discussed having this hypermatrix colloquium, for instance, and Carlos, in situations such as this, we can always take questions of this sort and hold some forum with the people who are also working on it and ask them, this is what we want to do. This is, there's this prospect of this particular spectral theory that we've considered, and we can at least aggregate some opinion from other people who are there, where they say, oh, well, if you wanted it for this particular purpose, you could consider this. There's this thing you could do. Maybe there's some paper that we haven't heard of. Yeah. Maybe they're working on something right now.
Absolutely.
So I would say, instead of just, and I'm not accusing you of saying like, let's just drop it, right? But I'm saying,
yeah. Okay, sure.
Right. But instead of dropping it, I think the thing to do would be to bundle all these questions together, and then when we hold this colloquium, besides just being, collegial and et cetera, we can use colloquia such as this to make more informed decisions about, whether or not some of these particular research questions are worth investigating or not. Because you never know, maybe someone's on the verge of publishing something about it, or maybe someone wasted their whole career on it and it's like, oh my God, don't even touch it. Well, it'll be good to ask.
Absolutely.
Okay.
My comment was purely in the scale of days in the near future. Right?
Yeah.
So,
and it's good. It's good. It's good to hear that you're thinking about it in this way. It's responsible.
Anyway,
okay. So
I think this is.
But you do have a suggestion.
Yeah,
so,
I have a much more promising direction that nonetheless leads to a pretty open-ended and kind of weird problem, or but let's see. So
weird. Okay,
this comes from the following observation. So we have the usual correspondence between graphs and matrices, right? Like this is we've discussed it several times. So given a graph G, I can associate some matrix A. Now we've been discussing, and this is kind of part of the problematic with Nick and I had a long discussion about maps of hypergraphs, right? So we want to, there is some tension at the computational level how to implement exactly what we mean by a map of hypergraphs. So for the context, let's just look at the example of a map of graphs in a conventional sense. And so if you have a map of graphs, normally what you mean is you have a map of the underlying vertex sets. Here, X and Y are the underlying vertex sets of two graphs.
Okay.
And you want to say something like phi is an assignment in general that maps things like this, right? So here, G is some edge on the vertices P and Q, some labels, right? Some indices for the vertices, and phi maps it into some vertex on R, right? So the question is as follows. So clearly, both G and R have their adjacency matrix analogs, right? So these are A and B. So they are n by n for A and m by m are the cardinalities of the vertex set. And so the question is, how do you relate these two matrices when you have a graph map between them, right? That's kind of the question here. And so the observation, remember that this index contraction is basically this logic checking, right? Like you're summing over means you check for all of them. It's like existence of, and then times is basically this conjunction that you require several things. So let's think for a second what it means to have a map between vertices to begin with, right? A map between vertices is basically some relation between vertices. So these are I just call F, right? And so you say that the vertex I gets mapped by the vertex map of phi, which I call little f. Sorry, I guess I should call it capital F, but whatever. You say this is true when you're actually mapping these two vertices, right? So
Yep.
So if you were to write a formula, and I guess it's written out here, so I mean I'll just talk over it. What you want to say is like, okay, the image of this map, right, is going to be a new graph on the same vertex set as the target graph, and you're going to have, Bij is the question: is there an edge of this new graph between vertices I and j? And so what you say is like, well, first of all, I need to run over my vertices p and q, because if these are generic vertices on A, and the question is, so the answer of is there an edge between I and j? The answer needs to be if some of the edges from my source graph is mapped into it, then there will be, right? So how do you express that? Well, first of all, you check for all edges in your initial graph. That's it. That is, check existence for OPQ for APQ, right? That's saying I'm going to check all my edges, right? And then what you're going to do is you're going to say, well, are these edges being mapped into the ones that I'm specifically asking for, which is I and j? And then you say, that means that you have to say that I gets sent to P and j gets sent to Q, right? So that's why I kind of put this here, which is and, right? And F is just the relation, again, a Boolean valued thing that gives you one when I gets sent to P in that exact way. So you're summing over P and Q, meaning you're spanning your entire graph, and you end up, I mean, if everything is simple and just Boolean valued, you end up with either a 1 or a 0 in B, and that gives you the existence of an edge. So if you look at this formula in detail, right, and you now reinterpret it in linear algebraic terms, what you find is that you have this very natural conjugation operation, right? So this is the natural transformation of matrices in the realm of matrices. If you forget about graphs, this is exactly how matrices should transform. Like, I'm sure a lot of people are familiar with general linear transformations, or orthogonal transformations, or invertible transformations, and things like that. That's how you transform a matrix, right? When you get a change of basis matrix or something like that, the way you act on a matrix is by conjugation, right? And so this is, again, another good justification of why these linear algebraic tools are natural in graph theory, because you have these formulas that naturally pop up. Okay, so this is kind of review of something that works for graphs, right? But the important thing here, again, always looking at the eigenvalue problem, or how to generalize this. The thing here is that F is a rectangular matrix in general, right? It relates something that is n by n to something that is n by n, right?
Right.
And it does so in this very natural pattern, which we are very familiar with because it's conjugation, and every group has a conjugation and all these kinds of things. I mean, bear in mind that these things are strongly non-invertible, right? Like, I mean, this F is some general matrix, right? Some rectangular matrix need not be. I mean, it's not even, doesn't even make sense to us whether they're invertible or not.
Sure.
So let's move. So in particular, just here, reminder, when phi is an isomorphism, so you have a graph isomorphism, then F happens to be an invertible matrix. Then F is n by n, and then it just corresponds to an invertible matrix when you have a graph isomorphism. Okay.
Got it.
So then, for our problem, we now have some kind of 3 graph. So in this case, it's just order 3 hypergraph. So it is captured by this hyper matrix. It's just a 3 array, and we have basically the same issue. Okay, let's consider a map of hypergraphs that sends H to S with underlying vertex sets Y and X, and let's try to build the same thing, right? Like, let's try to build what's happening here. So you construct basically the same formula.
Yeah.
You say the question ijk translates into the question pqr, and then you say if and.
Yeah.
Right. So, okay. Now,
But
the issue with this is that you cannot write something like this anymore.
yeah, right, exactly.
It doesn't correspond to a natural times transpose or anything like that. Because I mean, the way I would write this, if I'm just discovering this formula for the first time, I would say, well, this is some kind of A is in the middle, and then F's are coming in like three directions, right? And they are kind of attaching to it, and then this gives me a new whatever B, right? This is the end result is some kind of B, right? That would be my natural sort of notational way to do this.
Yes.
Right.
Yes. Yes.
And it's very clear that you can no longer. I mean, obviously, if you just isolate, say these two, right? So this is clearly, F contract A at the positions, at the appropriate positions. So in this particular, atomic instance, that's a matrix multiplication. That's a ordinary matrix multiplication there. The problem is that if you take that as a matrix multiplication, then you end up with that, same thing here, same thing here. So you have this sort of like, these things don't talk to each other, and you have this matrix multiplication. So if you were to express this as some kind of tensor network, then you would really get this expression, right? Like this triangle expression where your F, you have the A in the middle, and
okay, you're gonna do it again.
You have something like this, right? Now the problem is, we don't have an algebraic tool that captures this. In the graph case, we had this transpose and contraction, which is multiplication, that just gives us this conjugation operation that is very common and everyone uses, and we have all these theorems about it and so on. In this context, we don't have that thing. So
there's no nice tool for that, but you can still decompose it into tensor product and
contraction.
Dot product. Yeah.
Yep, absolutely.
You don't have to contract it. It's like every contraction you can just decompose into a tensor product and sequential product. Dot product.
We're calling the same thing. Dot product is contraction, right?
Yeah.
Yeah.
But you can still write it as a product without index notation.
But not uniquely.
Yeah, not uniquely.
Yeah, that's crucial. So absolutely. It's not the problem here is not that I'm writing indices. That's not so much the issue. The issue is that there doesn't seem to be one algebraic operation that just tells you, oh yeah, this is exactly what you're doing. And remember, you might be lost in this explanation, but remember, we come from something that is extremely unique and single in hypergraph land, right? In hypergraph land, all we're doing is mapping a hypergraph to another. That's all we're doing. Yeah. So suddenly in hypermatrix land, we have some multiplicity, arbitrariness, some kind of gauge freedom, that, right? So, anyway, so this is basically the problem that in general, there are more ways to do these things. Like there are more general hypergraph operations that you can define. I just went for the kind of most primitive one, which is just taking maps, which I actually never really thought about too much since the last couple of days, and this is already posing some kind of ambiguity issues. Now, I think that the main ambiguity is in ordering. And I think that, as Nick says, and this is a perfectly well-defined operation, right? Because and we know it's well-defined because it comes from a map, right? So if you're ever worried that you're not defining things well, you just go back to a hypergraph, map things with a map, and then output the hypermatrix, right? Now the question that is kind of deeper, and I'm trying to go at, is that the hypergraph operation here is kind of leading the algebra side, right? In this case, we're sort of relying on the hypergraph structure to generate more algebra on the side. So I think this is kind of my mantra in this context, right? Like I am mostly relying on hypergraph structure to generate algebraic operations. And if you sequentialize, you might be wondering, why did I put ijk in this order, and why you choose this particular order? Well, it's one order, right? It's not the only one. And if you permute things around, you're certainly going to change your explicit matrices, but you're clearly doing the same thing, right? So there's this gauge freedom. There's two gauge freedoms, right? Like there's the permutation gauge freedom that is usually there, and then there's this extra gauge freedom that somehow, that comes from the fact that you're doing some graphical contraction that doesn't boil down to something sequential, right? That it's kind of independent because it has three legs, so whatever happens to leg 1 and 2 doesn't really speak to what happens to leg 3, right? So that is kind of the entire problem. Like in the usual tensor notation, like some people might be wondering, but this is nothing new because I just see a tensor, order 3 tensor and order 2 tensors, and they're being contracted. I don't see anything new here, right? The problem is that in the previous case we had just a natural operation. Objects were internally composed, right? Here we can't really do that, right? Because everything has to be indices up and down, right? So you're basically just saying, well, what can I do here? I can put all the indices up and down, and if I contract A with F, it becomes now something that has 1 index up, 2 index down, and depending on the order that you do these contractions, you go over different spaces of tensors, right? Because depending how the order you choose to contract, you're going to end up with different raised and lowered indices, right? So there is.
And is it too naive to ask if you can simply invent some form of ternary composition or contraction? Is your point that even if you try and think of, what's your view on that?
I think that's kind of what it's suggesting. It's crying out loud. It's like, you can't boil me down to this binary contraction.
Well, this is your thing. You're like the first non-binary mathematician.
Not
in the normal way.
Well, isn't it like if you imagine a tensor with 3 indices, and then two tensors with 3 indices. One has 3 covariant indices, another one has 3 contravariant indices, right? If you compose them sequentially using a dot product, would it immediately suggest that you just contract all the corresponding indices that match with each other? You don't have to invent anything as a notation, right?
Well, but so okay, let me put it this way. Let me actually put it this way. So remember how in this case I had to say transpose here, then times A, then times F, right?
Yeah.
That's kind of what we're missing notationally. I don't think
it's all those F's, right? You put one of the indices back, one down, one up, right?
Yeah.
Their tensor product would make a tensor with 3 up indices, and then you just sequentially compose it with A.
Yeah.
You can write it uniquely in a way without any index or summation.
I mean, but that expression that would be unique it will depend on the choice of. Again, the problem is not so much that there are indices being summed in the expression, right? The issue is that if you want, we want to convert this into some kind of internal operation, so we have an algebra, and then in that algebra we can do the spectral theory, right?
Mm-hmm.
So we don't even have this for the conjugation. It's not like we usually call it a separate operation when we do the sandwich product, right?
Yeah, because it reduces to the binary operations, the unary operation of transposition and the binary operation of multiplication, right? That's why
here when we reduce to arbitrary, right? If you just have more than 2 indices contracting simultaneously, and there's no ambiguity how you compose them, right? As soon as you have three covariant, contravariant coming together.
I agree. There's no ambiguity. Yeah, I agree. There's no ambiguity how you contract them as long as you're keeping track of where each index goes. I mean, that I completely agree. But the question is, can you find an internal operation in some space of tensors, of all these tensors that you have some freedom to define, right? The question is, can you find some operation within some of these spaces of tensors, internal to these spaces of tensors, so that this operation is a map, it's an endomap of this. Well, in this case, it's actually sending one tensor of one kind of another tensor of a different dimension, but of the same kind, of the same order, right? But if you think of just endomorphisms, then everything becomes like this question of, can you be endo with the operations? Because the construction is clearly well defined. Like there is no problem here. Like you're contracting index 1 with index 1, index 2 with index 2, index 3 with index 3, and these things are independent of bases because they are pairwise contractions. There's no ambiguity in this formula, right? But that's not the problem. The problem is, can you make it into an operation that somehow resembles an algebra, so that you have a more or less obvious path into spectral theory? And the issue is that how do you choose? Like, you can just boil it down to, how do you choose the order of contractions and transpositions, right? I mean, this problem is present here. You can choose two orders here. You can put one index first or one index second, but that basically just transposes the whole thing, right? That's always the case with matrices. You can transpose everything, and it's technically different but equivalent, right? Because it's an invertible thing, transposition. But here there seems to be more freedom than just that. Like you can transpose things in several ways.
Well, that I still don't understand. It's like, when I think about how things compose here diagrammatically, it's like matrix composition is not really different from any more like n-dimensional arrays compositions.
Yeah.
Like you compose them in a similar way. And I still don't understand what is the like fundamental difference there. Is it only when you have to consider this spectral properties or what?
Well, the main problem is we want to do spectral theory, right? Like that's our objective. We want to have something. So you want to. I mean, spectral theory can be formulated in several ways. One of the approaches is to say your object equal some algebraic identity, right? Or proportional to some algebraic identity, right? And try to find spaces where this is true and things like that. Right. So if you want to do that, you first have to have an algebra to begin with, right? Some kind of operational context to do these operations. I mean,
you have linear algebra in all of those cases. So I don't understand what kind of algebra it's like even your different products, they still decompose into a linear algebraic operation. There's no new operations there.
That's not true, because the cone product, for example, or the blades product, doesn't decompose into matrix multiplication, into ordinary matrix multiplication, because they have this three-way index contraction.
Well, you can still write it as a glue matrix multiplication. You can like put some spider in there in between.
Sure, yeah. I mean, you can put some deltas if you want. Yeah, sure.
You can still write it as a matrix multiplication. That's what I still can't understand.
Yeah, but it's like saying you can always have the incidence matrix expression of any hypergraph, right? Like, but you might lose the algebraic structure that is there, right? Like you can do it technically, nothing's stopping you. But you fail to see, like here. I mean, if you had a candidate, like my point is, if you have a candidate, like if your knowledge of linear algebra in this context gives you a candidate for an identity here, like, well, for an operation to begin with, something that looks like an algebraic operation, then by all means, like that's kind of the problem here, that linear algebra doesn't seem to be suggesting one single construction, because there's this S3 sort of symmetries of three indices, kind of many different choices.
Is it because the spectral properties used in the matrix case assumes an eigenvector, right? You're constructing one index, but when you want some spectral properties of a three-dimensional array, you have to have some eigenmatrix instead.
Well,
Right,
that's
you have
one
to-
choice. Yeah, that's one choice. That's a
Okay.
possibility. That's one choice. To go, okay, I'm gonna regard my three matrices as matrices of two matrices, right? Like that's one choice. But the other choice was this other case of I'm gonna take two matrices to take a vector that's gonna produce a vector. So now my pairs of matrices, my pairs of cubical matrices are going to be my operators in this context, right? So the entire point of having maps represented with this is that composition of maps ends up being multiplication of matrices, right?
Mhm.
And so if you have the spectrum of a graph and you map it into a different one, like you're basically just doing a linear transformation of the entire spectrum, right? So the algebraic structure of composition, which ends up being just matrix multiplication, is kind of carrying the spectrum over, right? It respects the spectrum in this context.
Okay.
So anyway, I mean, I didn't want to have it like, I don't have a conclusion to say, oh yeah, this is it. Like, I just basically have many ways of finding these things, and now what should we do? Like, one thing that is obvious to me is, as James just said, we can just take this thing primitive, right? Because we're gonna do things computationally, and start to run experiments in the way of saying, well, this map, we have this hypergraph. We take the adjacency hypermatrix, and then we just map it to all the possible hypergraphs that are isomorphic to it, and then we try to get the pattern finitely, right? I mean, this is a possibility, but I mean, it would be nice to have some kind of theoretical prediction of what we're gonna find there, instead of just kind of generating. Okay, let me see this. Put it down here.
Well, we've almost run out of time, unfortunately. I mean, it seems as though the kind of the stakes of this discussion between Carlos and Nick, which has been very nice, by the way, is, effectively, I think Carlos is wondering to some extent, does this finding of his kind of justify this invention of this kind of ternary contraction, ternary composition, or can Nick identify some way in which this can be done where it's not necessary to invent this new thing? And I think so far Nick has made a number of suggestions, but Carlos still seems confident that
So Nick,
use of kind of prior techniques won't exactly resolve this issue.
like, my point is not so much that what Nick is suggesting is less or more likely. My point is that I'm not getting so there's no problem to solve initially. It's more like we need to state the problem to solve, right? So it's like pre problem solving. It's like you have to state the problem to solve, and what I'm missing here is not answers, but what I'm missing is questions. It's kind of weird, right? Like, I am missing.
But it seems like you've outlined some serious problems, though, Carlos.
Well, I mean,
maybe they're not precise enough. But you've at least begun to outline.
Oh no, yeah. The progress has been made. I mean, it's not that this is like completely vague, and we'll see where it goes. So progress has been made, but like my pushing back to Nick's comments is it's not that I think traditional tensor algebra is completely useless or anything like that. I mean, it can clearly represent all this stuff like efficiently, but the question is, how do you express the multiplication in this particular cases? Like, so just anecdotally, very quickly, one of the products that I introduced in the previous meeting was this fish product, right? When you contract things in this particularly sequential way, and the idea is that in that case, it turns out that by the pattern of contraction that you're doing, you end up with a product, that, when you do this kind of three triangle pattern, it turns out that this is actually analogous to this kind of pattern where you have matrices that just go in these directions, right? In a directed.
Yeah. I see that.
In a directed graph, right? So it turns out that when you actually look at the contraction structure, you end up with something that looks precisely like, if this is ABC, it looks like A times B transpose times C, right? So your ternary product, ABC, actually breaks down into a unary product, meaning the transpose, just a unary operation, and two binaries, or the same binary twice, right? So it happens that, and from this, you automatically get what kind of algebraic property it has. You automatically know that you can take these pairs as single operators because they are just multiplication by matrices. So the spectral theory of this is just the spectral theory of matrices, because all you're doing is multiplying matrices and transposing it. There's nothing new in this context from conventional matrix algebra, right? At least in the fundamental sense. And so, again, the contraction pattern here exactly matches this. And again, there is some gauge freedom of how to order stuff, and you actually have 4 different ways of indexing it if you want to do it with indices. But the problem is there doesn't seem to be anything that is equivalent here, right? Like in the cone product, for example. Like the cone product is just multiplying things in a completely fundamentally ternary way, and there doesn't seem to be any way of like saying actually this is multiplying, contracting here and here. Sure, if you put a delta in the middle and you like this kind of spider, then all contractions just become pairwise contractions with deltas. But I guess that kind of misses the point of like saying, yeah, that's literally the same thing because you're just contracting by identity. It's like, right? So it's not a problem of how to encode it, but a problem of what it tells you algebraically, so that you can say, oh yes, I'm safely in this land, right? So yeah, I guess my bottom line here is I'll just try to make this work like this explicitly, right? Like this is one algebraic operation that takes A to B. This is well defined, right? So maybe this I just have to take face value and just ask the eigenvalue question in terms of these matrices, right? Like F is a map that will send the eigen information of A to the eigen information of B, and there will be some compositionality in the process. And you can clearly see that this thing is multilinear because it's made of multiplications and contractions. Like there's no mystery there. So yeah. Anyway, but this was just one example, by the way. So there's all these adjacency based operations, which are like this fish or like the cone and so on. This was just based on maps, right? So just to illustrate what kind of problems you run into. Nick, okay. You had a problem. Maybe you want to mention that in the last 10 minutes, because we did start late. If you want to stay for, because the stream has been going for only 50 minutes.
Well, maybe briefly.
Yeah.
Just a fun visual thing in trying.
Just to conclude from this, so there are 2 things. One is with respect to the first problems that Carlos was posing regarding the spectral theory, we should pose those to the attendees of this hypermatrix colloquium. And Carlos, I'll chat with you about that tonight, about us starting to organize that. And on the other side, that was a good summary of this problem. We obviously didn't pose a strong problem or address it within the scope of this meeting, though I'm not sure if any of us really expected to. We should continue this privately on the Discord, etc., chatting about this.
Yeah.
Because I know that there's more to be said about it. Okay, and now we're going to pivot to yet another thing, which is some other problem. Okay, Nick. So, what's your problem?
Well, I have this. The problem is the visualization problem. We're trying to build some new hypergraph visual stuff, right? Visual tools that looks more like I don't know, just looks nicer. And the idea was to do some bubble growing of a hyperedges. Instead of just have polygons in 2D, in 3D, you just imagine that they have some thin film stretch between those vertices where the hyperedge goes, and then you blow bubbles from the center or something, so that they form some kind of minimal surface instead.
Seems interesting.
And I've been searching of
By the
how
way,
we-
yeah, just a quick comment on that. So the reasoning for this sort of bubble or surface visualization is that at a glance you will be able to get. So basically, unary order 1 edges will just be sort of balls, little solid balls. Then you will have order 2 edges will be lines. So they will be mostly straight, right? And if there's multi, there'll be several like curving to represent more than one. And then anything that is order 3 or higher will be this kind of, it will be sort of based on a polygon, right? So you want the vertices to kind of lay on a polygon, right? In a plane in 3D. And then between those, you have some kind of film, right? Some kind of surface that is kind of stretched. So it's kind of a curved polygon, right? Like this sort of a concave polygon, right? Where so that you have sort of empty space between the actual sides of the polygon, which will be order 2 edges if they exist, right? And the actual higher order edge, right? So this way you can, and the idea of blowing as bubbles is that if you want to represent several edges on the same sort of vertices of the same order, or well, maybe different orders, you have to kind of stretch them and push them around so that they don't intersect and they clearly represent the different edges, right?
I'll probably have to see it
this
in order to.
Yeah, we'll have some examples soon.
But it's okay. It is interesting.
At this point, it's not even clear how but this bubble film, soap film even makes sense. I don't know. But right now I'm just looking for some tools for how you would just play around with optimization problems like that. How it would just start with some mesh region, do some. We had a project at the summer school that's similar to that, where when you just start with some surface mesh and you evolve it. And this is the similar thing. You start with some. I found some code in the Mathematica Stack Exchange site that does this minimal surface estimation. You can, for example, this one, if you start with this surface, it's not and fix the boundary. The boundary would be these two circles, right? You fix this boundary, and then how would this surface evolve if you want to minimize the surface, the area of the surface, by the fixed area, and you run it, you get something like this.
Yeah.
It depends on how much iteration you do. If you do like two holes in it, like this, more holes on the, you can.
Then it's gonna.
Right? You can play around with this, but it looks like a bubble. But it's not
it's
sure
cool.
how to apply it to the actual hyperedges.
And Nick,
Because I want to apply some force into normally or something.
Yeah. So I guess you can't put the boundary to be just a collection of points, discrete points.
But how would it represent a hypergraph? That would be what points exactly?
No. So I don't know. Maybe I miscommunicated what I meant because, like, maybe.
Well, this is not directly applicable to the hyperedge yet.
I know. Yeah. But I mean, I think Richard, when you mentioned this, I think Richard understood that there would be a bubble that actually encompasses, that contains spatially the vertices. I don't think this is the idea. At least this is not what we discussed, Nick and I. I mean, I'm not saying that's a bad idea. I'm just saying that it's not what we had in mind. What we have in mind is essentially, if your hypergraph is simple, right, then basically all your edges are straight. They're flat. Right? They're just basically contained in planes. Now, if you're not simple, then you want to express non-simplicity by clamping on top of the same plane. So you kind of have to blow up from the plane, right? So you have to kind of curve away from the plane. That is kind of the simple plane. So the skeleton of any hypergraph visualization should be some kind of simplicial set, right? Where you have just basically a collection of polygons that for a given order of a hyperedge, you get that order, that number of sides of a polygon, right? And so, but the problem is, you don't want to. The only point of having this curved surface thing is that you don't want to communicate visually the edges, the straight edges of your polygons, because they might be mistaken by some lower order edge, right? So that's why you kind of, for higher order edges, you sort of make this elastic rubber material instead of a straight polygon. You just curve the sides convexly, right? Sort of, no, concavely, right, inside of your shape, and that way you can have several. You can have many edges incident on the same set of vertices, and the vertices, if there's no binary edges between them, they will be naked, right? Like there'll be empty space between the vertices, because everything will be in the surface of the higher order connection. And then you can optimize for intersection between edges and things like that. I mean, that's like a different transparency and so on.
It's hard. I don't know. Like my idea was to use this soap film for hyperedges when they have multiple duplicates of vertices, basically. So that was the idea, I think, was the original one, right? If you start with the polygon, like with five vertices, for example, this is the hyperedge, but your opposite vertices actually is the same vertex. So how do you represent it? You pull these vertices together, and if that surface was made of some elastic material, that would bend it in a way that it's visually appealing. Right? That was the idea.
Yeah, the problem is that to use the soap algorithms, you would have to specify some kind of boundary.
Yeah, so that's why it's not applicable in this sense. But
yeah. I would say we don't worry about loops.
Wait a second. I just want to, because I haven't been following this conversation and wasn't even aware that you guys were doing this. Are you guys discussing the problem that Nick, you wanted to discuss, or is there some further issue? Because we've only gone so far deep into your notebook. Was there something that you wanted to discuss in particular, or
there's not much? It's just there's nothing else there. It's just my playground notebook.
Yeah. Okay.
I mean, these functions, I think. I mean, there is this visualization problem, and then we were discussing some other technical thing about maps, but we can leave for next time, because that's I mean that's a very nice, so just to talk over that picture, that's a very nice rendering of a hypergraph, in my opinion. But what I would change is, like, when you look at that visually, it kind of communicates that the triangles have hard sides, right? I mean, sure, the other arrows are colored and the sides are black or whatever, but like the idea is to try and visually convey that if the edge is curved, so there's no straight path between the two vertices, then there's no edge that is pairwise between those two vertices, right? So instead of having those straight triangles, you have this sort of like I don't know, imagine like some kind of stretched out fabric between 3 points, right? It gets this kind of curved minimal surface kind of shape,
like
instead
a cell.
of a straight triangle, right?
Sure.
So that's the only point. That's the only thing that's different from this visualization, right? That it's just giving some subtle geometry to higher order edges, so they communicate that they are higher order and not pairwise.
Yeah. Yes, that makes sense. Guys, I have to run.
Yeah, no problem.
Unfortunately. Yeah. Wow. What do you guys want to continue?
You want to stay, Richard,
discussion?
with Nick for some minutes if you want.
Yeah, why not?
Okay. All right. Thanks, guys. See you later.
See you later.
Bye.
Yeah, we can continue for I don't know, 15, 30
I was
minutes.
about to mention that I also had this idea. If you have this minimal surface tools, whatever, set up, can you actually, if you start with a sphere, for example, can you just put all your hyperedges on the surface of that sphere, like make a hole or other way around, the complement of the sphere, and then kind of make your hyperedges actually as cubes between all of those. I know how would you stretch it? Like, I don't know. Basically, even two vertex edges, just two order edges would be like a cube, right? It's like those string diagrams, but for hyperedges. This kind of things, how that would work.
Yeah, that's fine. I mean, I guess like that's a possibility. It's, I don't know. I feel like because there's a choice here. I mean, do we use volume or not volume, right? Like that's one of the branching points that we can use. Like, do we, because you could go, binary, line, ternary, plane or surface, and then quaternary, you have volume, right? With the simplices of the right dimension, right? But I think like what the good use of 3 dimensions is you embed these arbitrary planes in 3 dimensions, and you have a lot more room than lines on the plane, and so and obviously lines in 3D as well, and so you arrange these polygons and planes in space with much more freedom, and so you try to fit all your information in planes and lines in 3D, right? Because this surface that you're saying will be some kind of volumes for everything, right?
This is like a surface point that makes more sense to render dual of the hypergraphs, not the hypergraphs directly. How we look, how it's done here, for example, when your pre-order hyperedge is a polygon, but when you take a dual, when each of the hyperedge is a single point and an actual vertex. If you have, for example, with this cubing, the hyperedge of order 3 would be represented as this, the cobordism thing for this in the string diagrams.
You mean like a pair of pants?
Yeah, that would be look like a pair of pants.
Well, but for that you have to blow up. That's not so much dual, but that you have to blow up a point to a circle, right?
Yeah, each vertex is would be a circle. Yeah.
Yeah, actually, I mean, this is out of curiosity. There's nothing to do with this, but I actually developed this thing, and we called it the tunnel algebra, which is basically, you imagine, so it's basically a hypergraph of circles where your vertices are circles, and your hyperedges are knots, are basically 2 manifolds between these circles, right? So they're basically like these cobordisms. It's higher order cobordisms, right?
Yeah.
So, but I think that's kind of a stylistic choice that will be interesting to do. But I don't think that like blowing up vertices to circles will make for the standard rendering of a hypergraph. I mean,
well, maybe that exactly will help to distinguish all of those different symmetries for hyperedge, right? Well, your pants would be. It's like, does it make sense to tie pants into a knot if you have some symmetry on your pants, which is not just directed?
I mean, thing is, you can have any knot in the middle, right? Like you can have a 3 or however many.
You can make a hole. You can make like a hole.
Yeah.
If you start with pants, you have 3 holes. But now you have to identify one of the vertices with another vertex. You bring those holes together, but you leave the hole in the middle.
Yeah.
Right. So that this is like.
Yeah, I mean, I should show you. I mean, we have a full algebra with this. It's like the operations are basically that. Like surgery and cobordism and like, and it's actually we actually used it as an example of a higher order algebra as well, because these things are compositional, right? You can surgically attach these things together, and some of them, like you say, they're handles, and they basically just collapse the thing, and it flattens, right? Some kind of identity properties and things like that. So yeah, I don't know. But I doubt that going to blowing up vertices to circles is going to be like the.
Well, but maybe that's not even the point. The point is that maybe why we always represent hypergraphs in this way, but not the dual notion.
No, but I mean, no. I mean, the dual notion is very interesting, but I'm not saying. I'm not seeing how the blowing up to circles is the dual.
It's not the dual. It's easier to render the dual version with circles if you want to do it.
Well, but
Like really.
I mean, the problem is if you have circles, you're gonna have, you know, when you have two triangles meeting in this context, or even two lines meeting, or two or three, you're gonna have these intersecting surfaces in 3D, right? Because they all share the same circle, so they're all gonna be like sharing the boundary that there. So when they are embedded in 3D, they're going to intersect.
Well, the intersection is the. Well, they're not going to intersect in a way that the paths intersect.
Oh,
Paths
wait,
look
wait,
like
wait,
that,
wait,
so they
wait,
have
wait,
three holes in there.
Wait. I see. You're making the vertices. I see. You're making the vertices into the junctions, right?
Yeah.
Yeah, but then in that case, you don't really gain anything from a spider diagram, right? Which is this sort of incidence graph that is labeled, right? Like, sure, it looks very nice. I agree. Like, it's nice 3 manifold or 2 manifold, you know, like this Riemannian surface, beautiful thing. But in terms of visualization, and I don't think you're gaining much beyond the because you would have to code it somehow, right? Because if you just render the surface, you lose all the information about edges and vertices. You have to color it somehow, say that here is a vertex or whatever. Like, you would have to say something, you know, that this is a junction, this is, and to me that basically just contains the information of the incidence graph of the hypergraph, right?
Yeah.
Which is fine, but that's kind of not solving the problem of visualizing the hypergraph itself primarily.
Well, it's hard to say without looking at it, but yeah.
Yeah, I mean, let me put it this way. I don't even need this elastic rubber band like kind of thing. That was just a suggestion. But to me, what's important is I look at the diagram, and visually there's a clear language of whether there is a binary edge between two vertices or not, when there are higher order vertices between them, higher order edges between them, right? That's my only concern. Like, I don't really care how to solve this problem. I just know that this is a big problem, especially in the context where network theory is so popular and everyone uses network diagrams and everyone, you know, simplicial complexes are so popular, even more popular than hypergraphs for higher order systems and people in the community and so on. So I just want to have some very clear, unmistaken visual language that communicates, oh, this is a unary, that's going to be clear because it's like a solid ball that has a very different geometry. This is a binary, which, you know, if you see like a string floating around, you know that there's a pairwise connection. It's a string. Visually, you identify that very clearly. And then if you have something that looks like a plane or even maybe a volume with transparency or whatever, like I don't have strong feelings about that. But it has to be like geometrically quite different from the other two, right?
Yeah. Well, I don't know.
Like, this is very good, but for example, like in this particular case, I would, if you maybe like, yeah, I guess the black edges kind of, like, the problem is when you have both of them, right? Like, it's not just even distinguishing one from the other, but like when you have both of them, like, it's very hard to see, right? Like, how do I see an undirected edge between vertices that also have a ternary edge, that also have a quaternary? Like, these things are very difficult to parse visually, right? If you just, everything goes on top and lines. So that's why I have this idea of like, you make the edges non-straight so they kind of repel each other. So the binary ones go straight and they have priority, they're sort of more central. And then the other things kind of stretch away from the shortest path, which is the binary path, so to speak, right?
Well, there are many possibilities here.
There are many possibilities. I'm not saying one is the best or anything, but So Richard,
Anyway,
did you have this problem with speed? And maybe you wanted to discuss.
Oh no, no, that's a separate thing. With this discussion here, it's like if you have restrictions, obviously it's a lot easier. If you don't have loops and multiple edges, like a higher order edge where all the vertices are the same, like a 3-order edge, all on the same vertex. And now when you have multiple of those, it seems to become very tricky to try and represent in a visual way. So I'm just thinking a little bit. Some idea popped into my head about doing like Cartesian products on the shapes. So if we think of vertices as circles, and if you have a 3-order edge with 3 circles, and now you take the Cartesian product of all 3 of those and somehow project that shape back into 3 dimensions, does that give us anything? But that could just be a whole lot of BS. That was just an idea that popped into my head. Like some kind of geometric construction where you do something to the vertices, as you suggested, you treat them as circles or spheres or some geometric object, and then when they belong to a high order edge, you take the Cartesian product in the geometric sense of those objects and now somehow project that into, but it's probably going to look crazy because, for example, if it's just two vertices, you have 2 circles. What's the Cartesian product of 2 circles? It's a torus. And if they're the same, then it looks kind of like a sphere. And if they are not the same, then if they're the same vertex, you could represent that as a sphere. And if they are not the same, then a torus, perhaps. But I don't think that's a very clear representation.
We were talking about this problem of loops, like self loops, self edges, things like that. And so my argument has been that we can actually entirely ignore self loops because we are going to do labeled hypergraphs eventually, right? The actual application of this rendering functions and all this formalism is going to be to have a skeletal hypergraph on which we put our data on top, right? So this multi-set data that we put on top, meaning you put several, whatever, like you can have as many redundancies as you want. If you have something like, I was saying to Nick this morning, you have like a graph, single edge graph, 2 vertices edge, and then you have a single vertex graph with 1 vertex, 1 edge, right? In both cases, I mean, these are clearly different structures, right? But if you, for some reason, only had access to simple graphs, right? So avoiding self loops, you can still represent the degenerate one, like the self loop one, by basically saying, well, label one is AB with edge and the other is AA with edge, right? Mm-hmm. So I think because we are definite, it's not like a sort of a patch for this or like a partial fix for later purposes. This is actually our goal. Our goal is to do these labeled hypergraphs anyway. I think that the rendering engine could just completely forget about self loops. I think that because remember the rendering itself is not necessarily the formal structure that we will work with eventually, right? Because these are meant to be. I mean, the example I was giving Nick earlier today was categories, right? Like if you think of categories as the commutative diagrams in categories are particular cases of directed graphs, right? Label directed graphs, right? So the idea here is that many people will be familiar in categories, although some people do write some self arrows because that's nice, just write an arrow. A lot of people will be familiar that when you actually do computations and you want to be very careful, you always say the identity arrow is A to A, right? Like that's how you write it. And category theorists are very quick to just duplicate as many objects as possible to make the diagram as spread out as possible, and so you can compose things as clearly as possible, right? So this is kind of the approach that your hypergraphs, I think, if you restrict to simple hypergraphs for the visualization, so you have the engine that renders simple hypergraphs, or at least non-self-loop hypergraphs, right? Because you can have several edges of the same kind if you want.
I understand.
I think that's enough. Like for the purposes of
Sure.
the project currently, I think that's enough.
Yeah.
So I think we can ignore that. We can actually ignore self loops for now.
For the visualization, I mean, we could still be doing rewriting or
Yeah,
you know, the
absolutely.
theory of rewriting, which includes self loops and multiple
Absolutely.
edges. But yeah, we have this translation to
Absolutely.
simple. Yeah.
Yeah.
And for the visualization.
The
Gotcha.
point was that Mathematica, or the way we're coding these anyway. Like if you think about it, when you write a self loop, right? You know, 1 1, and it's just like the pair, right? And that represents your undirected edge, right? The code actually knows that it's two different vertices, right? Like it has 2 slots. Like just
Yeah.
it just so happens that they carry the same symbol, right? So it's kind of the same idea, but on the theoretical level of what we are implementing, right? So for the visualization in particular, I think we can just ignore anything that is not kind of polygonal, right? Or simplicial. Let's put it this way, right? Like you can just assume that you are in this simplicial realm where everything can be parsed out, and you can just look at points, lines, planes, volumes,
Cells.
and so on,
Yeah,
right?
yeah.
I think
Yeah.
we can be very safe with that. Like I wouldn't worry too much.
I want to try this visualization for the dual, which is completely alternative way of doing it. It's like imagine the simple way, the simple visualization like this. We have a hyperedge, right? Every hyperedge is a circle. Okay.
Wait. Every hyperedge is a circle.
Yes.
Okay.
Okay. And you put points around it, like a circle points, depending on what order it is. If it's a hyperedge of order 2, you put 2 diagonally opposite points. If you have order 3, you put like a triangle points on the circle.
Okay.
And then because the circle, those points gonna represent an actual hypergraph vertex, right? You have to connect all of them. So all you have to do is just connect those vertices together in a very nice way. So it's not gonna be just a single line. It's gonna be like this branching line that like has branches, right? If you only have one incidence between 2 hyperedges that they share the same vertex, it's just a line. If you have 3 hyperedges share a vertex, it's gonna be like this branching line that like has this I don't know, crossing in the middle when the three lines meet in a way, and you can
Wait.
blend them together.
I've seen some visualizations like what you're describing in the literature for hypergraph visualization.
Yeah.
See if I can find some. Yeah, that's a cool idea.
I don't fully understand what you mean. So what are your edges in the end made of?
No. Hyperedges or the visualization edges. The line.
Hyperedges.
The hyperedges always are circles.
Circles.
So you just scatter them around, whatever makes sense. You know, that's the optimization problem, how you put
Sure.
them.
Yeah.
But then when the hyperedge share a vertex, you just connect them depending on how many, what is the degree of the vertex, how many or incidence degree of the vertex, because it shares, each vertex share many hyperedges, right? So vertex is just one continuous
So as in
branch.
so like a solid circle, like a disc, you mean for an edge?
Yeah.
Okay.
In 2D, it's a circle. In 3D, it can be a sphere.
No, wait. But when you say circle, you mean disc, right?
Well, you can show it as an actual circle.
But I'm confused because, like, say I have like a Treeforce, right? A Treeforce is a small hypergraph with 3 triangles, right?
Okay.
So I can visualize clearly a Treeforce. Now, give me the shape that your representation turns the Treeforce into.
Well, let's try to actually. I don't, can we draw?
Yeah. Just try to
Let's do
draw.
some drawing. Let's do this.
I have some examples. Were you meaning that the vertices are on the boundary of the circle or contained within the circle?
The boundary, right?
Hold on. So we have this Treeforce thing, right?
Oh,
That's the usual thing, right?
the animation is very smooth.
because it's within zoom, right? So this is the three hyperedges. 1, 2, 3.
Yeah.
The dual notion would be you represent each of those hyperedges as a circle
Yeah. So far so good.
because all of them are order 3,
Yeah.
right? You put like
3 points. Yeah.
each of them and just
Hmm.
connect them together
Yeah.
in the obvious way. So that I think that's
To show the identity of the vertices, you connect them with these lines, these branching lines.
So now what do you do graphically now?
let's also call this vertices B,
A-
E,
Sure.
and C.
So there's some duplication of the vertices, but you.
Not
Yeah,
duplication.
that's interesting.
E, F.
Well,
So,
I mean, C
vertex-
exists twice on the right.
A, B, C.
Yeah, and
D,
on
E,
the right,
F.
on the right-hand side, you have sort of repeated C in a sense in those two circles, but you could signify that with a line connecting them to show that.
Yeah, but you're gonna deform these circles somehow, right, Nick?
No, not necessarily.
Okay, so I don't understand the. Okay, so give me the give me the representation. I mean, you should be able to draw it, right?
Yeah, I'm trying.
Okay,
So-
just draw it. Just draw
so
it.
so
Don't
your
explain.
vertex,
Just draw.
vertex A, right? It should be just a line.
Yeah, sure.
Yeah,
Don't.
Yeah.
So we do it like this maybe.
yeah. That's kind of all I was saying about how they're duplicated. And when you go higher, you were saying something about splitting lines. So somehow I see.
Sure, but okay.
But this is not interesting because there's no vertex that share more than
Okay, then
More than two.
2 hyperedges.
do the windmill or whatever, like, or the cone. Just do the windmill, which is 3 triangles with 1 common vertex.
No, that's basically it, right? And you have some free floating pins that you don't have to connect.
Yeah, this is the tensor network.
Yeah, but if
visualization.
there is some, let's
Like just do 3 triangles with 1 common vertex.
do this floating,
No, that's the same. That's the same. Well, depends.
and I'll put it over here.
3
Right?
triangles with 1 common vertex would be 3 circles, and then
Because this B1 now shares
3 hyperedges.
Yeah.
Yeah.
That would like be this line would now be like this.
Yeah.
No, it's
So you,
split.
yeah. Mhm.
Okay, but okay. So then you're just. I mean, the circle thing is purely cosmetic, and then you're just basically doing the usual multi-line hyperedge representation, right?
Yeah.
Like
Yeah,
forking
multi-line.
line
Forking
representation.
line, multi-line, yeah.
Yeah, but
Make it smooth
sure.
as possible.
Okay, but that's very well, like a lot of people use that, right? Like, and I think it's extremely confusing because I mean, at a glance, everything is a mess of lines, right? If you have a slightly big hypergraph, everything looks like a line. It's extremely hard to tell the order of the line, right? Like you just see a line like going everywhere, and how do you parse? Oh, right, this actually branches in 4. You have to find the intersections, like where they fork out.
Well, you have to specify the hub, right? The hub would be.
Sure, yeah.
Well, it's an optimization kind of problem. Where do you put the hub of your
Sure,
vertex?
I agree.
Where it branches.
My point, yeah, I agree. My point is because the order of the edges in a hypergraph is what's most novel about a hypergraph representation, right? From other representations, from network representation, we have very good, efficient ways of doing networks, right? But doing higher order connectivity is not so efficient, right? So my point is that trying to bring to the fore and make it as prominent as possible the fact that you have higher order than 2 and distinguish it from order 2, I think is the priority. And if you just want to count, it's easy to parse something that looks like a polygon, right? Because you just count. I mean, intuitively, you look at a square, it looks a square, it looks triangle, pentagon looks pentagon, and of course, you lose resolution as you go up. But being able to clearly, visually identify like 1, 2, 3, 4, 5, 6, visually just parsing. But if you show me like several branching, can I draw like this? Like if you just show, this is 1, this is, or 2, this is 3, this is like 4, this is like 5. It's not like these regions all look quite similar, right? Like these hubs all look quite similar, and like if there's more lines going behind them and everything is like, it's quite noisy, right? It's quite a noisy representation. But like the distinction is between that and like this triangle, square, pentagon, whatever. Like I think it's much more like in your face, like this is a different shape. And my entire point was you have to have like things that triangles coexist with lines and coexist with squares and things like that. And so maybe you want to like bend them a little bit so that they don't quite overlap. And so it's, there's more air between them, air flows between the edges, they're not like completely pasted together, right? Like they're a little bit.
Yeah. Yeah.
It would look like some kind of spider web, in the end. Like, because, the whole thing would look like, my interpretation, now that we're here, is that, for the triforce, you do something like, these 3 points, external ones, and you have these 3 internal points, and then you do something like curve, whatever. This is terrible drawing. Right? And you do something like this. So that if you have now a pairwise, then you can do it straight, for example, and you can distinguish that this is filled and that's straight or whatever. Right? That's the entire idea of like stretching it a little bit like elastic. So there's no overlap on the simplicial boundaries. But it's kind of a tweak. It's just a tweak from the polygonal representation. I think we all agree that the polygonal was quite good. And this is just a minor graphical tweak from the polygonal representation. I'm not trying to like build a different representation. It's just like, let's tweak it a little bit so it does essentially what the polygonal does, but with a little bit better communication.
It's still weird that we were missing the dual notion, an automatic construction, right? An automatic plotting of dual version like this, right?
What do you mean?
It would be nice. So that the same the plot that does this dual representation too. I think I would do it. It's much easier at least.
But you mean the incidence representation?
No, the one that I draw, something like this.
But that's essentially the incidence representation, right?
Oh, it is, yeah, but maybe with more bendy bias. We'll see.
Yeah, I mean, I think, but that's, I mean, that's what you want, right? Like you want a set of, you want that two, instead of one set of vertices and then connections, you want two sets of vertices. One, the original vertices, the other, the hyper edges. And then you just wire everything in between, right?
Yeah.
Yeah. So, I mean, my point is that that's been done to death in some sense, right? Like, the problem of like wire diagrams has been worked on a lot. And in this particular case, you just have collection of vertices and collection of hyper edges as new vertices, and just you're gonna wire them. And I agree. I mean, I'm not saying it's not something that we should do. Like having a good visualization of that incidence graph would be great. But what I'm trying to say is that this is kind of a parallel representation problem from just explicitly representing the hypergraph, which in my opinion is what makes hypergraph better or distinct. I don't know if better. I don't want to sell anything to anyone, right? But it's what makes them distinct. It's like hypergraphs are this higher order stuff, and thinking in terms of triangles and squares and things like fit into these higher geometric shapes is what can actually help do something that is different from just wire diagrams, which is what everyone has been doing for 40 years in mathematics. That's the whole point. I'm not saying we shouldn't do it. It's just that having a direct, manipulative visual representation of this order 1, 2, 3, 4, 5, clearly distinct, and I think that's good. I think that's desirable for the system. And for sure, we should have function that, sure, incidence graph. There you go, and it's beautiful as well. And if you want to put like tubes I think it will be great because for the incidents, that's kind of cool, right? Like you see everything like tubes and to like express that, hey, they're not just wires, you know, they're not pairwise, everything merges. But they are just two different functions, right? Like the incidence graph and the explicit hypergraph rendering. Those are kind of independent. More thoughts, Richard?
It's a very tricky area. Yeah.
Yeah.
But I think the idea of only dealing with some restricted thing and casting our graphs into that form is a good solution.
Yeah. I mean, the other thing is we could work with transparency, right? I mean, we will have to do some transparency at some point just to make things clearer, obviously, but you could also use like volumes and just have like some convex sets or something and just use transparency. I just feel like that loses the blackboardness of the representation.
Yeah.
Like to me, that what's nice about a community diagram in category theory on a piece of paper or a blackboard is that it's very high contrast, right? Like it's like these are the objects, these are the things. My brain is looking at the more sort of highlighted stuff, right? And it's against that background that it's very tangible. I can feel I can touch them and move them around, right? And if we put hyper edges that are like transparent prisms and things like that, I think that's going to lose that sort of tangibility and you know. I mean,
yeah. The worst case being that you go to the bipartite graph representation of your hypergraph, which is just not interpretable at all. That's like the worst solution to this problem. So we want something over on this side.
Yeah.
You see what I mean? Like the
bipartite
in the sense that you have vertex vertices and edge vertices.
Oh yeah, the incidence graph.
Yeah, the incidence graph of a hypergraph, which sure that is a way of communicating the structure of the hypergraph, but it's like the worst choice, I think. That's the only point I was making. So we want something sort of.
Well, I agree. I mean,
yeah,
I don't know if I would say it's the worst choice, but it's certainly something that is low priority in that it just throws wires everywhere, right? Like instead of condensing. I mean, the whole point of hypergraphs is like condensing, coarse graining, and so on, right? So at the level of the data structure, no problem if everything is incidence matrix or whatever, that's fine. But like for visualization, we need to look at hypergraphs, right? I mean, otherwise it's almost like, why are we even calling them hypergraphs and not like networks that just, you know, labeled in some interesting way? It's like, sure, those are hypergraphs because they feel like. And I do think, by the way, I mean, probably I should have said this when James was around, but I do think that there is no standard, right? Like because there's no package, there's no software that you can just, Google, I want to do hypergraph stuff. That doesn't exist, right? So I do think that we have this opportunity to like create it and just make a very efficient, basic package of hypergraph mathematics, right? And again, it might not be like the most efficient to do huge hypergraphs or whatever, like huge networks in the beginning, but if it has good functionality for like labeling, representing diagrams and so on, it could be super powerful for like teaching, or like not necessarily teaching as in like undergrads or whatever, but like explaining, like representing something as like you explain this and you put your little 7 or 10 edge hypergraph that represents something, and it's like a nice thing. There's 3D is rendered, it's there, and like that's how I see this being useful. And obviously for all these algebraic rules, like the rewrite rules and so on for the research, these are going to involve like a handful of hyperedges, each of them, right? And those are the ones that we want to really look at and like have a rendering of. And then sure, then you can do the larger ones, and maybe we can have like a low poly versions of those where everything is straight and it's much more sort of like transparency based, and it's, you know, but the ones that are like the blackboard diagrams that you would draw at the beginning of a lecture is like they need to look kind of crisp and distinct and. But anyway.
Yeah, and certainly there's no comprehensive like hypergraph visualization toolkits or software or anything. Yeah.
No.
So there's a big gap there to fill.
Yeah, and not even, I would say there's no hypergraph, but there's not even like hypergraph functionality in general. Like there's no package where it's yeah, this is all you want to know about hypergraphs. Just these are all our functions. I mean, I would have expected that would be the case in the Wolfram function repository.
Yeah,
but it wasn't. So
in the chat, you may have not noticed, but at the very top of our chat in the current Zoom session, I linked some hypermatrix algebra package. It's Sage Math, but it has, and just whilst you were talking, I was kind of googling some of the keywords and things, and finding these papers.
Oh, this is the guy.
What was interesting?
I know this guy.
Yeah.
I mean, I talked to this guy.
Cool. What was interesting is this Bhattacharya Messner algebra, which is some ternary algebra.
That's
thing.
the cone.
I'm sure
That's the cone. That's what I'm calling the cone for short.
Cool.
Yeah.
And then there's this paper, Combinatorial Approach to Hypermatrix Algebra, and then some other. What was the other one? Oh, it was so some sort of approximate spectral. Well, this paper had this notion of eigenmatrix, which Nick had mentioned. So anyway, but yeah, this package.
Oh, that's cool. I didn't know. Eddie did the package for Sage. That's interesting.
Mm-hmm. So there's probably some things to like look at in there.
For sure. Actually, that's great that you found that, because I wasn't aware. He didn't tell me basically. I mean, we talked several times. He never mentioned it.
6 years ago.
6 years ago.
That was put online, so it's been around.
Does it tell you when he was online?
No, I don't think GitHub will do that. Oh, you can look at somebody's activity thing to see if they've...
Oh, updated in 2018. Interesting. But yeah, anyway, yeah, that's cool. That's very useful. I'm gonna open this up in the.
I can just put it in our Discord somewhere so that we all have a... In the WL functionality category, I'll just link it there under hypergraphs.
Yep. That's very cool. Anyway, Nick, are you on board with the distinction between like incidence graph, hypergraph, more geometric?
Yeah, it's surprising that we don't have like functionality to proper render it. It's like there's a hypergraph plot, right? It kind of looks like it, but it's more, but it's a direct version of it.
Yeah, well, I've been saying this many times, right? Like, it is surprising. There's no database of hypergraphs online, and there's like several databases of graphs online, right? So these are the kinds of things that I mean, James is not, for some reason, not hyper enthusiastic about it. Maybe because it wasn't his idea originally, but I do think that I mean, it's hard to find something like this, right? I mean, it's just a coincidence that we're all working on hypergraphs somehow, and then we now find ourselves with the expertise to actually develop these functions. On my own, I was thinking I have to do this sooner or later, and I thought I would do it my own. And then you guys happen to be in the same institution where I am right now, and I was like, okay, I have much better access to your skills, and I feel like there's this very obvious gap in functionality, in literature, in fundamental theory, like in many levels. But you know, and you know, this is not even a feeling or like a observation. It's like this has been confirmed by the people who run the websites where there's all these graph databases. They said there's nothing like this. We don't know, like, this is a missing thing. Like they've explicitly said it doesn't exist, right? Like, so I don't know when you will ever find, if the interest of the institute is to be positioned in the landscape of computational, service to science, general, and so on. I don't know how you would ever find a better fit than this, where there's like a very clear gap. There's a rising popularity of these hypergraph techniques in complex networks and things like that. And we have the expertise. We have the Mathematica stack. We have Nick's wizardry. We have Richard's experience with graphics and all kinds of stuff. And, I have my background in like pure maths in this higher arity, higher order stuff. Like, I feel like it's a very good combination of factors that's like, this is an obvious thing to put energy into, right? And try to make a little trench in the community where, it's our thing. It's like, yeah, these are our faces, people think of Hypergraph. Oh yeah, there's this nice package that you can do stuff with, right? Because I mean, this Sage thing from Eddie, it's hyper specific, right? Pun intended. It's like this thing does the Bhattacharya-Messner product, and you can do these linear combinations of skew fields. That's it. Like that's basically all it does, right?
I see. So you would want something more general that incorporates all of the diagrams you've shown.
Exactly,
so far.
but because it's quite easy, right? Like I just don't see like a big undertaking that will take us, months, or it's like it is quite ready to just be made. We just need I think it just needed someone or a team of people that saw, okay, this is what's needed, and let's just try to do it, right? Like, and let's debate what is the best way to express. I mean, these kind of debates are very good, like these discussions about, would you the wire diagram or like surfaces, and like all these things are very important, because at the end of the day there's no standard of how to represent hypergraphs, right? And we're going to be like breaking new ground if we find something that is quite good for some applications, because if they are good enough, then they're going to be quite standard, right? Moving forward. So yeah, it's that kind of, because if you look at the literature, hypergraphs are only shown in like explanatory kind of minimalistic diagrams, right? There's like network, and then you have like more, and there's like maybe a shaded area or something, or there's like a triangle that is filled or something like that, right? Especially if they are using this simplicial complex approach, then they're just simplicial complexes because this is just a common thing, right? But there aren't really diagrams or figures like graphics of hypergraphs, right? That just show. I mean, I guess the Wolfram Physics project had some, but the approach was just transparency, right? It's just like do some transparency, and that's it. And I think that we can do a bit better. Like we can improve a little bit because we don't have the goal of just writing huge millions of edges of hypergraphs, right? So anyway, I think this is a unique opportunity, and it fits well with like project that James had for this formal system emulation thing. It fits well with whatever we want to express visually, some other systems. I think it just makes a lot of sense, and we have all the expertise necessary. I mean, to me, it is like
it's a good
dream come true.
Good project that we can all work on different aspects of.
Exactly.
And from the algebra side, I guess it would be a case of like, you've really sort of set a different foundation compared to this Sage Math implementation, something that's kind of generalizes the operation, because this just deals with that one algebra, whereas you're sort of stepping back and you have a system which can now describe a whole kind of family or a whole range of algebras. So I guess it's about sort of building this hierarchy of definitions and functions and software tools in order to compose these things and recover these objects at the top. And
I mean, well, exactly. So the point actually is that you want to move away from sequential code or sequential language, right? You want to move away, like today's discussion, right? We had this instance where F was attaching in three different positions, right? And if our natural language for communication of these topics was naturally graphical, so that there's no problem to represent that way, there wouldn't be any discussion there. It's like, all right, that's it. So the point is that what characterizes operations happens to be hypergraph topology, right? Because I mean that was my entire presentation of one of these 2 or 3 meetings ago, right? Like I had this different topologies give you these different operations because you do this adjacency game and some details thrown in. But the general philosophy is you have some collection of topologies, just some hypergraphs in particular, like motifs, and those things determine algebra. So the idea is that even if your system is doing all the algebra, you have arrays or whatever, you're doing all this multiplication. I mean, actually, NumPy has functionality to do this, right? I mean, it has quite general functionality and it can do it. And I've used it in the past. But the idea is like, even if it does everything that in the background, or even if we actually use NumPy somehow, like, doesn't matter.
Are you talking about the Einstein notation tools that it has? That one.
Yeah. It actually covers this multi-index contraction, right?
Yeah.
So the point is, it doesn't matter how you compute it. The idea here is like the kind of game changer is the interface, right? If you're able to directly connect hypergraph representation, hypergraph manipulation, hypergraph operations that could be interacted with in a graphical interface, like putting some, points in a plane, and just like this website that we saw that you go and you draw the graphs. You can do the same thing with hypergraphs, right? You draw the hypergraphs and they are all superimposed, and then they go to 3D and they kind of float and they render, right? So the idea is if you can just do algebra that way, right? Like category theories do, right? Like they usually don't write long computations in terms of like F composed with G, composed with inverse of G, like I cancel like an identity. They don't usually do the algebrist work where they write long lines of computations. They usually just draw diagrams, right? So the idea here is to try and develop the tools for the mathematician that would draw diagrams of this higher order mathematics, right? That have more than just directed graphs, right? But obviously, if you just want to do directed graphs, that's perfectly fine, right? It would also do directed graphs. I mean, it would do category theory just fine, right? In 2D, 3D, no problem. Like this will be just fine because it will be part of this system. That's why I said between vertices there should be just a straight line, because we should recover like the standard directed graph or undirected graph story, right? So that's my point, that we have this opportunity to like build that kind of framework where you're using it to not do algebra, right? Like you're using it to reason graphically, and eventually also to compute graphically. I mean, obviously we're going to have computability functionality there. Like it's going to be possible to say, yeah, if you want to rewrite this whole thing using this axiom, then it's going to do it, right? And it's going to give you like a multi-way of possible rewrites and so on. But that's like further down the line. Just primitively, what we want is this blackboard, this glorified blackboard that just renders things effectively, right? I think that's the goal. I mean, and that's what I think James wanted as well with this. I mean, when I argued for hypergraphs for formal systems, is that you can always translate into labeled hypergraphs, and you have this common ground. So if you have a common ground, then it's just a formal, like a formal fact that you're just like, oh yeah, sure. If I organize sets in this way, and sure, it's a hypergraph. I think that's very weak. If you just say, you can formally argue that, because you can formally translate basically everything into everything, right? Like formally, everything is a set within a set within a set, or everything is some kind of diagram.
What's that statement? Is it everything is everything else?
Yeah, I mean, it's just, like in mathematics, you can do that, right? Like, okay, yeah, this can be formulated in type theory with this blah blah blah. Like you can do this all day, right? But that's not the point. The point is, it's not to say we love hypergraphs because they have hype in the name, but that we love hypergraphs because they can be graphically represented in a very striking, like distinctive way that you can comprehend as a human being, right? Which is basically because you can look at geometric shapes and sort of polytopes in space, and you can make sense of them, right? And you can outsource a lot of the algebra and formal structure to your visual reasoning and to your spatial reasoning, right? Which is the whole point of diagrammatic thinking in the modern history of mathematics, right? So anyway, I mean, I know this sounds like I'm trying to preach and trying to convince and trying to sell, especially for the audience who's listening, but this is the reasoning I have behind this, right? Like why you would want something that is very basic, but efficient, right? You don't want to, You don't want to like just solve something that is very sophisticated or like very big hypergraphs or very fast or something. I mean, sure, optimization is great, but like I think it's better to go after being basic and being great at the basic functionality, right? And just take it from there and see where we go. Right, guys. Closing comments, thoughts.
That's it.
Right, so you buy my my pitch.
Yeah, it motivates it very well.
Cool.
Yeah.
Very nice. Yeah, I don't think I will be in tomorrow's meeting, but I'll be around. So if either of you wants to meet, I'll be around tomorrow.
Cool.
All right, audience, I think that's it from us today. So yeah, thanks for watching. I mean, there's a few comments here, so I'm gonna post the usual community links. Feel free to check our social media, all that kind of stuff. Join our Discord if you want to ask questions, interact with staff members. Oh wait, I'm missing something on the screen. That was a collaborative exclamation mark. All right. Goodbye, everyone. I'm gonna
Bye.
close